Hey guys, let's go ahead and go over those exercises 1 through 6. For 1 through 5, it gives you a data set, okay? And it's essentially the same, it's the same data set that we worked on in the last example 2, except for now they've given you more time intervals to work with. So instead they were just going 1 second intervals, so 1, 2, 3, and 4 seconds. But now they're giving you half a second, 1 second, 1.5, 2, and so on. So we're basically just seeing what happens as the ball drops in at more times than at essentially double the times that they gave us last time. Okay. So the first question asks you guys to name 2 predictions that you can make from this table. Well, for this one, I mean, really, let's just say, well, let's look here at 2, okay? So after 2 seconds, well, it's gone 64 feet, okay? And at 3.5 seconds, it's gone 196 feet, okay? Or at half a second, it's only gone 4 feet. Okay? So that's basically all they wanted from the first question. Number 2 asks, what is a prediction that would require more information? Well, since we don't have a constant speed or constant rate, or if we're graphing it, a constant slope, since we don't have those things, we can only make predictions based on the numbers the table gave us, okay? So if we wanted to say, well, how far has the stone traveled at 2 3/4 seconds, okay, 2.75 seconds. That's not on the table, and we don't know the rule for the function, so we can't figure that out. We can't just plug 2.75, into some equation because we don't have that equation yet. Another one would be, if I want to figure out where it is at, say, 1.8 seconds or 1.4632 seconds. Basically anything that's not on this table right here, you're not going to be able to figure out unless we can figure out the rule or the function that this data is following. All right, number 3 asks, what is the average speed of the object between 0 and 3 seconds? So, and then it gives you the formula for average speed, which, we've done this before. So it's basically just the distance traveled over some time interval that they give you divided by that time interval, whatever that time interval happens to be. And so for us, going from 0 to 3 seconds, well, that's 3 seconds, okay? And if we look at the data, after 3 seconds, it's gone 144 feet, okay? So so our average speed is equal to, so let's see, average speed, get out of the way so you guys can see, is equal to the distance traveled over that given time interval, which we said was 144 feet, focus. So we said that was 144 feet, all right, and the time interval, well, from 0 to 3 seconds, we said was 3 seconds, okay? Okay, so 144 divided by 3 goes into 14 4 times. 3 goes into 24 8 times. We're done. Okay? So we have that the average speed over those first 3 seconds was 48 feet per second. And I'm just going to write. Seconds are usually just s. Now it asks, how does this compare to the average speed calculated over the same interval in example 1? Well, remember, example 1 was where we were assuming linearity, or we were assuming that it had constant speed, constant rate, okay? And so in that case, remember our function was y equals 64x, and so our rate or our speed was 64 feet per second. Okay, so that was different than this one. So, what happened to my 8? So somehow this one is going a little bit slower in the first 3 seconds than if it had constant speed. So in example 1, the average speed over any time interval was 64 feet per second. Okay, and so as some of you have hopefully predicted, the average speed is not going to be the same over different time intervals in this example. All right, number 4 asks us to take a closer look at the data, and then we're going to answer these questions. So basically, how many feet did the stone drop between a certain amount of time? Part A asks, how many feet did the stone drop between 0 and 1 second? So between 0 and 1 second. So it gives us a beginning time and an ending time, a start time and an end time. Okay, so what we're going to basically do is we're going to take the distance traveled at end time, and we're going to subtract off the distance traveled at start time. Okay, so for A, the end time was 1 second, and after 1 second, it's gone 16 feet. Okay. Minus the distance traveled at the start time. Well, at 0 seconds, it's traveled 0 feet. Okay, so 16 minus 0. All right, so we get that it traveled 16 feet between 0 and 1 second. Okay? Now for part B, the distance that it traveled between 1 and 2 seconds. Okay? So the distance that it traveled at the end time, so after 2 seconds, it's gone 64 feet. And we already said that the time it traveled at after 1 second was 16. Okay? And so 64 minus 16 is going to give us not 14, 48 feet. Okay? So now let's go on to C. 2 and 3 seconds. All right? Okay, so at 3 seconds, we have gone 144 feet. And then at 2, we had gone 64 feet. So we need to do 144 minus 64, and that is going to give us 80 feet. Okay? Okay, so at 4 seconds, we've gone 256 feet. And at 3 seconds, we said we had gone 144 feet. So 256 minus 144 is going to give us 112 feet. But we can look a little bit deeper into this, and there was a little bit of a pattern that I was hoping some of you guys might see. So let me erase this. I'm going to put all of the times on the board. Okay, so not only did we notice that the average distance over 1 second changed as time went on. So as time progressed, it started going faster and faster. So we had went 16 feet in the first second, but we traveled a whole 48 feet in the second. We actually traveled 80 feet in this second and 112 feet in the last second. So while all of these time intervals are the same length, they're all 1 second long. Since the stone is picking up speed, it's actually going farther in these later time intervals, okay? And there is a bit of a pattern between these numbers that maybe some of you guys figured out. And this is sort of hinting at a topic that we're going to learn about a lot later. And that is the idea of acceleration, which I'm not going to go into too deeply. But this is, in physics, this was what would be considered a constant acceleration problem. And what that gives us is that now the interval between these is actually all the same. And so maybe some of you noticed that from 16 feet to 48 feet, well, that was an extra 32 feet. But from 48 to 80, that was another extra 32 feet. And then finally from 80 to 112, that was again 32 feet. Okay? So while our speed is actually increasing, what this is telling us is that the amount that it's increasing is actually a constant. We're leaving this idea of constant rate behind, and so numbers are going to start looking, different. It's going to be harder to sort of see the pattern. There is some semblance of pattern if you look deep enough. Oh, all right, guys. Number 5 says, what is the average speed in each half-second interval? Yes, I know it says interval half-second, but sorry, I didn't write the book, guys. For example, the average speed over the interval from 3.5 seconds to 4 seconds is, then it gives you distance traveled over a given time interval divided by time interval. That's just the formula for average speed. Okay. But how we're finding that distance is just like we did in number 3, guys. We take the distance that had traveled at 4 seconds and we subtract off the distance that had traveled at 3.5. So 256 minus 196 divided by, well, the first time interval minus the second time interval. Or sorry, the ending time minus the starting time. So 4 seconds. So we ended at 4 seconds and we started at 3.5 seconds. So we're going to do 4 minus 3.5. Okay, and that gives us 60 over 0.5, which coincidentally is the same thing as 60 times 2. Which is 120 feet. So in that very last half-second interval, it's traveling 120 feet per second. Okay, and now it just wants you to do this for all the rest of them. I'm not going to go through every single one, but we will do like maybe the first 2. Okay, so let's do the interval between 0 and 0.5 seconds, okay? So again, we need the distances. So how far has it traveled after half a second? Well, it's traveled 4 feet. And then how far had it traveled at 0 seconds? Well, just 0, okay? And then we need to take our ending time and subtract off our start time. So 0.5 minus 0. Okay. So that's just going to give us 4 over 0.5. Okay, and so now we've got a fraction with a decimal in it. We don't like that. So let's see. So we have 0.5 is the same thing as 1/2. Okay. So which is the same thing as 4 divided by 1/2. All right, and now we're going to keep, change, flip. So keep, change, flip. 4 times 2 over 1 is just 8. Okay? So its average speed in the first half a second was 8 feet per second. Okay? And I'll do one more for you guys, because I think this is pretty self-explanatory. You guys, you're literally just going to do the exact same thing. All right. So let's just do B. So between 0.5 seconds and 1 second. All right. So after 1 second, it's gone 16 feet. After 0.5 seconds, it's gone 4 feet. And we need to take 1 minus 0.5. Okay, hopefully, guys, since, we're doing this all over half-second interval, for your denominator in every single one of these problems, you should get half a second. Okay, so last time we had 0.5 seconds minus 0 seconds, so we got 0.5 seconds, or half a second. Now we have 1 minus 0.5, which is just going to give us 0.5, okay, or half a second. All right, 16 minus 4, though, is going to give us 12 over 0.5. Okay, we do the same thing. This is 12 times 2. All right, so between 0.5 seconds and 1 second, or the second half-second interval, we see that its average speed is 24 feet per second. Okay. All right, so let's jump into part H here for number 5. Now, so it says compare the average speed between each time interval. Okay, so I've written on the board the average speeds for each half-second time interval. Okay, and technically, if I want to, I'm not going to add H since we're doing H right now, but technically, remember that the last half-second interval is the one that they gave you. The average speed during that half-second interval was 120 feet per second, okay? So what is the pattern that you notice between each of these numbers? Okay, and so again, we're looking for patterns, even though the sort of pattern that we are used to seeing is not there. Even though that one's not there, we can still sort of find patterns in the data, okay? So to get from 8 to 24, switch colors here. Well, that's 16, an additional 16 feet per second. Well, to get from 24 to 40, again, that's another 16 feet per second. 40 to 56, 56 to 72, and so on. And you can check that the math works out, but I promise you it does. So this is, again, that idea that I was talking about before, where your speed is not constant, but the rate at which your speed is increasing is constant. Okay, so each half-second interval, we're increasing speed by 16 feet per second. Okay, so in the first second, we're going some speed. In the second half-second, we jump up by 16 feet per second. In the third half-second, we again jump up by 16 feet per second. And again, and we just keep jumping up in those intervals. And now this number would be different if we chose a smaller interval. But again, we can't consider those intervals because we don't yet have the rule for this function. Okay. Okay, guys, this is the last one. So it says, is there any pattern to the data of the falling stone? This is definitely going to be new, and it really just has to do with playing around with the numbers and seeing how they are related. But what I do want to do real quick, though, is just jump back to exercise 5, part H, where it asked us to sort of look at the, how much it was increasing every half second, right? And we did see that that number 16 came up. So maybe we're going to keep that in our minds. We're looking out for a 16. We also saw like a 32, so maybe something that relates to one of those numbers is going to be in here. So let's just start by looking at all the numbers. Okay, so we've got 16, 64, 144, and 156. Okay, well, I can definitely see in the first two numbers there's a factor of 16. Sort of easy to see, right? So with 16, well, we can just pull out, that's just 16 times 1. Okay, so obviously it is 16, so it has a factor of 16, right? Well, 64 also has a factor of 16. It's actually 16 times 4. So just kind of going off of that, I'm going to say, well, hey, maybe there's a 16 in all of them. I'm going to try and factor out a 16 of the other two. Okay, so the next one was 144. So we want to say, is that a factor, or is 16 a factor of this? Can we multiply 16 by something to get 144? Well, what about 256? Can we multiply 16 by something to get 256? As it turns out, we can. So 144 is actually 16 times 9, and 256 is actually 16 times 16. So if you got this far, great. That's awesome. I am super happy with you if you guys got this far. But we're not quite there yet, okay? So let's look at these numbers that we're multiplying by 16. So we've got 1, 4, 9, and 16. What could possibly be special about that sequence of numbers? 1, 4, 9, 16. Think about our table up above, okay? And see if you can relate the times to these. So remember, so this was, change colors again. So this was at 1 second. This was at 2 seconds. This was at 3 seconds. And this was at 4 seconds. All right. So see if we can relate these numbers. 1 second and 1. 2 seconds and 4. 3 seconds and 9. 4 seconds and 16. All right. So now that I've given you guys a few seconds to think about that, well, let's look. So, well, 1 is just 1. Okay, whatever. Well, 4, well, if you divide it by 2, you get that. So maybe that's a place to start. But let's go on and see if that pattern holds. Well, so I've got 3 and 9. Well, if I divide 9 by 2, I don't get 3. Ah, rats. Okay, so that was not the right solution. That's okay. Let's go back and start over. Well, how else can we get 4 from 2? Well, I do know that 2 squared is equal to 4. So if I take the time and I multiply it by itself, so 2 times 2, I do get 4. Now let's see if that pattern holds. So if I take 3 and I square it, or multiply itself, 3 times 3, hey, look at that, I get 9. Hey, we're on track. Let's see if this holds out for the last one. Well, 4 squared is 4 times 4, and hey, that is 16, okay? So using this, we can sort of come up with a rule for this data set, a rule of how to get basically to predict where it is after any time interval. So okay, so let's look at these equations, right? So the numbers here, that was our distance traveled, okay? So distance, okay, we usually just call that our y, okay? And then we had this sort of crazy 16 here. That was a factor of every single one of them, okay? So, let's see. I'm going to start the equation down here. Y equals. So we know whatever we do, before we do, we have to multiply by 16, okay? Great. Then we had our number here, which we said was our time multiplied by itself, or our time squared. Okay, so time, well, we usually call that x in the ones that we've been working on. Okay, so to get our distance, we need to take that factor of 16, and then we need to multiply it by our time, and then we have to square it. Okay? Now you have your rule, your function. And as you can see, we have a variable multiplied by a variable. Okay, so we have x times x, or x squared. So right off the bat, we know it's not linear, even though we already knew it's not linear. But now it sort of matches up. Like, it's a good thing that we didn't take this data set that we said was nonlinear and then somehow get a linear equation. That wouldn't have been good. So what we got is not a linear equation. It is still a function, and this is our rule, and it really does model what happens to objects as they fall through the air here on Earth.